So we're talking about Hecke operators, which are, or in other words, relationships between flags on finite sets, and we invented a notation for them, a matrix notation for them. And let's just let's go over exactly how the matrix notation works. So, can we give an example? I guess we did the same example that we did last time. So let's see, what was one example of a relationship that we had here? We had
Put 2, 1, 1 down to the diagonal.
yeah, that's too vanilla. I want something.
So I got 1, 1, 1, 0 down the first column.
Ready? One?
Down the first column, 1, 1, 0.
Yeah.
And then we can go 1, 1, 0, 0.
1, 0, 0.
And then 0, 0, 1.
Okay. And I just want to explain how this works. So you can think of a flag on a finite set as a labeling, or a labeled partition into pieces of size 2, 1, 1. So this is the Young diagram 2, 1, 1. And this one over here is also the Young diagram 2, 1, 1. Yeah, we're not there. And the way I think of it is that you can think of, so what we're going to do is we're going to have two labelings on the same set, and we're going to see how they relate to each other. So the set is a 4-element set, because we have 4 boxes, and we're going to have two labelings. You can think of both, I'll think of both labelings as colorings, but I'll think of one as like the color of the person's hat, and the other one is the color of the person's shoes, or something like that. So I can call this like red, blue, green, red, blue, and green, or it doesn't matter what color you use. That would be like hat, that would be shoes. And so we're saying that there's one person who's wearing both red hat and red shoes. One person who's wearing blue hat and red shoes. That's the way to make it. And on the other hand, when you get used to how the notation works, you can sort of think of it in a less elaborate way. So this is just saying, so this kind, you can think of this kind of partition as an ordered pair. This kind of partition is an ordered pair. And when you think about what this matrix is saying, it's really saying that the second coordinates are the same of the two ordered pairs. That's the relationship between the two ordered pairs. Which means what? That means that somebody who's wearing both a green hat and green shoes. So it's a fact, a pretty obvious fact, that this system notation works. This is exactly the kind of notation that you need to describe all possible relationships between flags on finite sets. It's a significantly less trivial fact that this notation actually works in a more general context. That it's actually good for describing relationships between flags on finite vector space, finite dimensional vector spaces over finite fields as well. One way you can tell that that's a less trivial fact is that the equivalent fact really doesn't work if you think about relationships between 3 flags. Well, right here we're dealing with relationships between two flags. One, the first flag and the second flag. And we're discovering the fact, or I'm stating the fact, that the classification of the relationships, of the binary relationships, works exactly the same for the flags on finite sets as for the flags on vector spaces. And a warning is that doesn't keep on holding all the time. If you start studying ternary relationships between flags, then the flags on vector spaces, I think they start becoming more complicated. The ternary relationships start becoming more complicated than the ternary relations between flags on finite sets.
But you haven't given us any reason to consider ternary relations thus far, right? I mean, we're only considering binary relations because we're considering intertwining operators from one to another, and there's two things. Yeah, well, it depends. It depends on your experience. If you're mostly used to functions of one variable and operators of one variable, then yeah, it makes very much sense to think about binary things. Or again, if you're used to binary predicates from logic. But you probably had experience with all these things, functions of multiple variables or multilinear functions, those like multilinear operators, and also predicates of higher arity in logic or something. So we're a little bit prepared. It shouldn't come too much of a shock if at some point we start thinking about ternary or higher order relationships as well. But it turns out that there are some special facts about binary relationships that don't hold for higher order relationships. And this is one of those facts. The fact is that the classification of the binary relationships is somewhat mysteriously easier than the classification of higher order relationships, specifically in the case of flags on finite dimensional vector spaces. So again, this is a notation for Hecke operators. These relationships, which you also think of as intertwining operators between permutation representations, linear operators of a certain kind. So again, in some sense, I don't know, ironic or something that we're representing a certain kind of linear operator by a matrix of numbers, even though we don't seem to be doing it in the normal way of representing a linear operator by a matrix of numbers. So you said something about the ternary relations, and is a circumstance under which something like that might arise, like an intertwiner between a tensor product of two vector spaces to another vector space? Yeah, sorry, that's so. Right, so that would be, well, that's a, I don't know. No, that's exactly right. Okay. That's exactly right. So this is the notation for operators, and we want to think about how to compose the operators. And we want to think about perhaps how to use this notation to help us compose the operators. So we're going to think about some examples of composing these Hecke operators. So I guess I'll start out with some really small example. I guess I'll use examples like this. Maybe we can try composing this Hecke operator with itself. So I'm going to think of it as like this is a relationship between the coloring of the hat and the coloring of the gloves. And this is going to be a relationship between the coloring of the gloves and the coloring of the shoes. So I guess we're imagining there's like 4 people corresponding to the 4 boxes for the Young diagram. And they're wearing hats, gloves, and shoes. This matrix is telling us what's the relationship between their hat colors and their glove colors. This matrix is telling us the relationship between their glove colors and their shoe colors. And we're supposed to try to figure out the relationship between their hat colors and their shoe colors. See. Now, we may have mentioned this before, that you're not guaranteed to get a single answer for the relationship. But can you figure out what the relationship could possibly be? Let's see. I'm trying to think of a way of stating the problem to make it more intuitive what you're trying to. Yeah. So. See, we have a relation. We have a relationship between an ordered pair and another ordered pair, B prime, G prime, and then another ordered pair, B double prime, G double prime. And I'm telling you the relationship between this ordered pair here, and I'm telling you the relationship between this ordered pair here, and I'm supposed to try to figure out the relationship between this ordered pair. So in other words, BG is the person who's wearing the blue hat and the person who's wearing the green hat. So yeah, I really am making a mistake with this line. Okay, so this is the line I'm supposed to. Okay, sorry, I really confused it. So
the D and the B prime must be the same. That's what you're trying to say.
say it again, which two?
So the relationship that we were given is that
D and the B prime.
In D and B prime, I'm not talking about D and G prime.
I mean, it depends on what the way you're ordering your coordinates.
Oh, well, I think you can see how it's supposed to go over here.
If it's hat, comma, gloves, and gloves, comma, shoes, then the gloves and the gloves are the same. And you're asking what about the way now the same person can wear a red hat and have white gloves?
No, you're thinking the ordered pairs backwards. This is an ordered pair of 2 people each wearing a hat. The second one is 2 people each with a glove color. The third one is 2 people each with a shoe color. That's not an ordered pair of the one person is wearing a blue hat and a
Oh,
green.
it's not that way.
Yeah, this is hat, this is gloves, and this is shoes. Hat is up, look, now like hat, gloves, shoes. And so yeah, so I think sort of that G is equal to G prime. Can you read it? There's G. Yeah. This is like, maybe I should put like, maybe I should put like prime there or. So what it's really saying is that G is G prime. And this one is saying what?
G prime.
G prime equals G double prime, right? So, what's the relationship?
So first off, we should have G double prime is G. We should have a 1 down the bottom corner.
Yeah, there's one person at least one makes this,
At least one
right,
that has, yeah.
right. And then we still figure out 3 other people, I guess.
Something like that.
So,
And I think that's where the variation is in the 3 other people, where we can have, like you said, there's more than one answer here.
okay, so if you come with any answer, what would be any one
So
possible?
any one answer would be exactly what we had before.
Yeah, that certainly works. Right, that's one possibility, but the only relationship between these two here is that this G is the same as this G double prime. We have to have G equal to G double prime because, you know, G is G prime and G prime is G double prime. So we're getting like that.
But one thing we could have is, you know, we have to have B and B prime different, and we have to have B prime and B double prime different, but we could have B and B double prime be the same.
Exactly. So that's the other possibility. I think that's the only other possibility. And what does that one look like?
Well, that's our diagonal 2, 1, 1, I think.
Oh, is that right?
And then all the ordered pairs are precisely the same. Our ordered pair is precisely the same ordered pair.
So when we combine these two, we get a sort of mixture of this one and this one. Those are the 2 possible relationships that you could get between the coloring of the hat and the coloring of the shoes. That's just supposed to be one simple example. We're supposed to streamline this process and make it into something that we can easily calculate or something like that. That's what we're trying to do now. Well, or something like that. We're trying to understand this process in a more streamlined way. So this was very much a toy example using a small number of people. I'm going to give a larger example using more people. And in fact, I think what I'll do is, I think I'll use the same example, but I'll just blow it up into a larger amount of people. I'll tell you what I mean. Where does it be?
Jim, over here.
That's right. So all I'm really going to do is I'm going to put extra zeros on everything. 200, 100, 100, 200, 100, 100, 100, 100, 0, 100, 100, 100, like that. So same thing over here. Okay, and now we're going to try to at least partially calculate the composition of these 2 Hecke operators. The actual complete answer might be sort of too laborious to write down, but we can calculate a lot about it. question to try to figure out. Well, okay, let's see. All right, this question I don't even really know the answer to. Are there any of these numbers that are just really easy to figure out? What the answers are going to be? I have the idea that there might be we have 400 people, and 200 of them are wearing red hats, 100 are wearing blue hats, 100 are wearing green hats. Same for their gloves and same for their shoes. And
Seems like this corner is green, the green hat, green shoes, bottom corner, there's no way for it to vary. This is equal to that, I feel that it has to be all net people down the bottom.
is that right?
Yeah.
You got 100 here?
Yeah.
And does that mean it's going to be 0?
Yeah, it means those are 0 and those are 0 because, and this. And you can see in the matrix, you can see that there's absolutely no people wearing green hats and red gloves. And there's absolutely no people who are wearing red gloves or also wearing green. So there's no way to get from, there's no path from the red hat down to the green shoes or whatever. The green hat down to the red shoes. There's no path from the green hat down to the blue.
I think that's right. I think we're just kind of lucky in this particular case that we know that there may be many possible answers,
Yeah.
but they will all, I think, look like this. But now we can see what the possibilities are over here. And let's see, what would be, can you figure out what would be the most number we could get up here? What? Is that right? We get 200?
Because there's only 200 people wearing red hats.
So this could happen.
Yeah.
So this is the one that gets the most up there. Okay. What would give the least up in this upper left-hand corner? What's the least possible you could get here?
100, I think.
No. Actually,
Oh, you could have the middle corner, the middle square occupied or something.
yeah.
Give me a number.
No, I think 100 really is the least in this case.
100
Because you've got to have at least, you've got to have a total of 200 people wearing red hats, right?
200 people wearing red hats, yeah.
Okay. Well, down in this case, there's only 100 people wearing blue shoes. So at most, only 100 of those 200 people could be wearing blue shoes. Yes. So that means the least number of people that could be wearing the red is 100. It has to be at least 100 people with red hats that are also wearing red shoes.
That's right. That's right. So
2 squares are less equals 100. 1 square is 200.
So basically, the two examples we had, the two we had, we left these as ones everywhere,
yeah.
were in some way our most and least for that corner. But because we had such small numbers, there was no options in between.
You're right. Yeah.
So
That's an interesting point.
the largest number we had there was a 2. The smallest we had was the 1 there.
Yeah, that's interesting. That's right. So you're saying it sort of resembles our entry from the previous smaller example.
Right. So at least the large end and the small end of this.
Yeah. So right. So in that small example, those are the only possibilities. So one of those things had to happen. But now, think about the case we have now, the larger example, and you told me some things that could happen. You could get 200 out here, which is on the high end. You could get 100 out here, which is on the low end. Well, what would, would you bet that you're going to get 200 up here? Or would you bet not to get 100?
No.
What's the most likely thing that you're going to get?
It seems like it's in the middle there, 150.
150.
I mean, that's just, you know, without a lot of thought.
Multiplicity is free.
Yeah, without a lot of thought,
Without a lot of stuff.
you know, maybe it's a thought, we want to change that, but it's an initial place to start thinking about it.
Well, if it is 150, can you tell what the others would be? I guess you can tell what the others are. Once you decide what the 150 is, then everything else is 4.
Yeah, so 50, 50, and then,
Yeah, the, 15 more.
oh, actually, hold on, can we repeat that?
50, 50, and 50, and then you ask if it's possible.
Okay, yeah. 50, 50.
50, 50 are determined, therefore that is 50 as well.
It has to be.
No.
No, it's 50 in the middle.
Because the sum of the squares should be 400. So then add a 5, then you get 50. And now you ask if it's possible. See, the row sums and the column sums add up correctly.
We can, in this example, we can actually get any number between 100 and 200 in the top corner.
Yeah.
And once we have that number, the other three numbers are actually determined completely by that number.
Yeah.
I think that's right. But, so are you saying, so this was your answer, so with, as you said, without thinking about it too much, this is where you would put your money on what the most likely answer is.
Yeah. And actually, I would, thinking about it now, actually, I don't think any of the possibilities have a higher probability than the other possibilities.
Well, I'm not sure what you mean by most likely.
If you think of it as a probability, there's no reason that this should happen more often than one of our other cases. Like I said, this was my guess without thinking, and now thinking about it. I think it's a random.
So again, so you think that of all the possibilities,
I think of all the possibilities, they all are equally likely to happen.
Okay, that's interesting. So, okay.
Because the way I think about it is that the other three, so all we're doing is we're coming up with what are the possible things to put in the top left corner.
That's all we're doing. And everything else is complete.
The other three things, the other three numbers at that point are then completely determined by what that number is. There's no variation once you choose that number.
But I wish I could convince you with some sort of computer simulation or something like that, because I think your gut answer first was more correct. I think that there's actually, I think if you actually do it, you'll find that it almost always comes out really close to this. What?
Why?
Okay, now I'm actually gonna lean back the other way now that you mentioned that, because
Have you made an argument for him?
yeah, I have an argument. You think of it like how many possible ways are there to have everybody with red hats wearing red shoes? Only one possible way. But how many possible ways are there to be 199 people wearing red hats and red shoes? And one person
The
like that.
people themselves are not interchangeable. That's why you should be counting multiplicities. And because otherwise,
Something like
what you are saying is like otherwise 150 and 149 are the same, would mean that basically you just have 100 copies of the same clone and you're just near them. Whereas now you're saying, no, they really are the same pieces.
Yeah, maybe we should try to clarify the rules here a little bit.
Yeah, maybe there's.
You might have to
I think
explain
maybe there's a
about the
rule.
rules.
I have a question. I mean, I really didn't know what you meant when you said what's the most likely. And then when you said, when you do it, you think you're more likely to get this. But what do you mean by do it?
Okay.
When you do what?
Okay, there are several interpretations that we can give here, and I was being sloppy about what interpretation we could use. But I'll try to give a pretty definite interpretation right now about how to interpret this as a probability problem. So, I guess the simplest way would be just to make it a conditional probability problem. So, in other words, we have specific 400 people, and they're not interchangeable. You know, you can tell who they are. And you randomly toss the hats on their head. You randomly toss the gloves on their hands, which is a lot harder than tossing the hats on their head. And shoes on feet and by the arm. And then you check to see whether the relationship between the hats and the gloves is like this. And you check to see whether the relationship between the gloves and the shoes is like this. And if it is, then you go ahead and count that example. If not, you shoot everybody, call in another bunch of 400 people, do it over until it works.
So we're saying in a situation where these two relationships hold, what's the probability that this relationship also holds?
Yeah, so what's the conditional probability, given that this relationship holds and this relationship holds? That's the condition. What's the probability then that this will also hold? And the original sort of random sample was this random labelings of the specific 400 people.
There's a lot of, yeah.
So now you get size argument now?
Yeah, sure. Now you expect it to go to those normal.
Yeah, there is
What is that in the
something
normal set?
or something like that, yeah. Yeah, so I think it gets very highly peaked for this possibility. And of course, we're talking more zeros at the end of the number, so we're getting more highly peaked. So let's try to pursue formalizing this guess or calculation, halfway between guess and a calculation, that we've gotten right here. So again, we didn't get a full answer for all the possibilities. We discovered
we know what they are.
What's that?
We know what all the possibilities are. We just don't know the multiplicity.
Okay.
Yeah, but I think like I said, most in this case, we should go to calculate actually directly.
Yeah,
Okay, sure.
And actually, simply enough to write it down like right now, in the sense that everything is completely determined by that one square.
Yeah, but how many of them are square are there? Or do
Well,
you determine that as some binomial coefficient?
Yes.
Okay. Then we can,
So you can determine the possibilities and the number of times possibility happens by that.
we can completely do this right now. So let's do it.
Completely the answer for all of.
What are the states and what multiplicity, relative probability do they occur?
Okay, I wasn't going to do anything like that, but if we really want to do it, we can.
You put an X there and I want
So we put an
I don't want to put an X in place that, I want to put 100 plus X.
and yeah, 100%.
So I can write the sort of generic answer here?
Yeah.
That's it. Yeah.
So the generic answer is going to be,
100 plus N.
no, it's going to be 100 plus N. And then the other three squares around it are going to be N.
No, that's 200 minus N, 200 minus N.
200.
No,
200.
it's not.
Oh, you're right. That was 100.
Sorry, 100
minus
100
10.
minus 10.
100 minus 10, yeah.
But
Then it goes left one in the middle ones.
The middle is it. 100 minus N.
And this middle one is 10.
Yeah.
And the center square is 10.
What is this,
And
N?
That's 10.
And then,
And the bottom corner is still 100 and zeros we had before.
Okay, and you were trying to describe for me a
probability for that.
probability for that?
Exactly, and the probability, and I'm going to even move the shift to say, if I choose this middle square,
Yeah, exactly.
if I make my choice on that middle square, that's going to determine what the other squares are.
Yeah.
And so,
Okay.
and so, how many different, so the question is how many different organizations of this whole thing, it's, so we.
As a function of N?
Yeah, as a
It's
function of
100
N.
to Z, right?
Yeah, so 200, okay, so in one, yeah, so how many possible, what he's saying is, whatever number N is, the number of multiplicity of that happening is 200 units. Or 100.
100 units.
100 units, we're only going up to 100. N goes from 0 to
So
100.
look at any column sum.
So you're saying that the 100 Q's, is that how it's written?
Yes, over 2 to the 100.
Well, that's the multiplicity of that one happening, we want probability over 2, yeah.
Should we try and think, let me think for a moment about whether we should do it in terms of probability. There's sort of annoyingly different normalization conventions that you can use when you're doing these kind of calculations, right? And sort of normalize probability to be total, the total probability to equal to 1.
Yes. So then you divide by 2 to the 100. Yeah.
Yeah, but I sort of, I'm not a physicist by any stretch of the imagination, but I hang around with physicists sometimes, and they're very sloppy about normalizing their probabilities. They don't always normalize their probabilities to equal to 1. And I tend to do the same thing sometimes.
What do they normalize?
What?
What do they normalize?
They often just normalize it to be what? To be,
Whatever the total is.
yeah, whatever the total is. They often do that.
That's not normalized.
And then they consider, and then they sort of elevate the normalization factor that they have to use. They pretend that that's like an important physical quantity. They call it the partition function.
I don't really understand exactly what they do, but, I guess I'm just sort of warning you that I might fall into that habit sometime of not normalizing my probabilities the way you expect us to. Okay, you are trying to normalize the probabilities?
Sure, so you want to divide it by 2 to the 100, which would be the total possibilities.
Called the random distribution.
Yeah, I mean, to relate it to the other thing.
Well, the what, Jim?
The random.
I know it, right. Yeah, I wasn't really thinking of this connection at all between, right, so we've now mentioned the binomial theorem in, I think, two completely different ways. Maybe they're not secret.
So, we got Leibniz's example that there's one square that could be determined with
Yes,
relations. With
yes.
every other relations we have, we're gonna have to use multinomial.
Yeah, I was trying to lead us in a direction where it would just be so completely annoying to actually do this calculation that we would all be happy to use certain kinds of approximate answers instead. So I'm sort of annoyed that you actually all managed to somehow come to an exact answer. Well, but I'm going to go ahead and try and encourage us to figure out how to figure out the approximate answer. Where is the sort of peak of the normal distribution or whatever? And I guess in this case it's over here. So, well, I'm going to go get the 2 by 2 matrices for a moment. Let's have red shoes and blue shoes, I guess. And red gloves and blue gloves. And red shoes and blue shoes. And I was going to do another numerical example. Maybe we should have to just do a sort of symbolic example, you know, like A, B, C, D. What? B. Yeah, I know we're getting B. Is everybody like that? I know some people don't like it.
Just go to red and green.
Oh, alpha, beta, gamma.
Not
Yeah, these are names of colors. These are not names of variables. These are abbreviations for colors. These are variables. Okay. And let's see. In order for this to even work, we need some constraints here. Can you tell me what constraints we need here? I mean, for example, the total number of people, A plus B plus C plus D, that's equal to E plus F plus Q plus A. Right, that's what we need. But we actually need more than that, right? What do we need in order for this problem to make sense?
Well, like A plus C equals E plus G.
A plus C?
No, that's not necessary. We had that in this example because we composed the same relationship.
No, it was the same Young diagram here and here, but you don't necessarily.
What do we need?
You know, A plus B equals E plus C, R prime.
A plus B?
Oh, yeah. Look at the R prime. A plus B equals E plus G. And that's enough. If you're adding the totals and totals, that's
And the same thing the other way.
Oh, okay, right. Or I guess right. And the reason they're right, the reason they're the same is they're both equal to what? R prime?
Number of R primes. You don't know the
Number of R primes.
And then we need the same one for B prime, which is C plus D equals F plus A plus G.
Then you do not need the one for the total, because that will just be the sum.
Right. Okay. And
Of course, they're all non-negative. A, B, C, D, E, F, G, H are all big.
yes, and they're integers.
Yes, natural number.
Non-negative.
Yeah, so that's not right.
Non-negative natural. Non-negative integers.
So let's see. Will it make sense if I ask again? What's the answer can be a bunch of possibilities that look like, you know, R, B, R double prime, and double prime. is there any way that you can give me an answer if I ask you, like, again, what's the smallest you can get here, or what's the most you can get here?
Yeah, I think we can kind of say that this.
There's a min max something.
It's just really annoying, we just give up.
No.
I don't know, I mean,
I think we can say that, so it can't get bigger than A plus C.
Yes.
Oh, no, but I think there is a min-max on here. I think
Yeah.
it's the max of, it can't get bigger than the minimum of A plus B or E plus F.
Okay, but that's not complicated enough that I don't want to.
Right, exactly. That's
It's
what I'm
the
saying.
sum of two minimums, I think, or something.
Yeah,
Minimum
yeah.
of A comma E
It might
plus
be.
minimum of C comma F.
Well, I was expecting the minimum two something. Yeah, but,
Yeah,
I think I've already gotten to the noise I think problem, because
Yeah.
the formula is not too complicated.
Okay, first of all, so that needs to correct the thing.
Say that again?
The multiplicity needs to be corrected. The probability is fine. But the multiplicity, both the numerator and denominator, at least the numerator should be multiplied by 200 to 100. Because you have to identify the green lights first. I mean, the 100 is not fixed, or is it fixed?
Oh, yeah.
Oh, it's fixed.
Sorry, green light.
Okay. Okay, it almost sounds like you're going to try and get us to do the exact answer again, so I want the approximate answer. I want you to, tell me where you would put your money on what these answers are going to be. Just like I would put my money in this case, if I had to bet on one of them, the one, and if I got paid, even if I was a little bit off, I would bet on this one. This is the one where the distribution is going to have a peak. In this case, I want to know, again, where's the one where the distribution is going to have a peak? Any ideas about how to figure it out?
No, even with that, it seems like we're gonna have some minimum and maximum gains going on.
I'm not expecting that. I'm expecting it to be easier than that. Like, think of it this way. Think of it this way. Think of it like, think of it like you start out just seeing their hat. Or the people are lined up, and you can only see what their hats are. And then at this point, the curtain is lower or something, so you can see their hats and their gloves. And then at this point, the curtain is lower even more, so you can see their hats and their gloves and their shoes. So at the first stage, you just see their hats. You see there's A of them have red hats. No, how does it work? No, R of them have red hats. How does it work?
A of them have red hats and red gloves, right?
No, but we just have A plus C of them have red hats. And B plus C of them have blue hats.
Yeah.
Right, okay, right. R of them have, right. You look at the hats and there, R of them have red hats.
That's why you don't know the art. So then you start saying B and then.
All right, well,
This ninja color is green. How
What do you got to see over here now?
Oh God. How about P for photo?
I'm gonna try and use the numbers.
Okay.
So the number of red.
Okay.
So the number of red have red hats, and the number of blue have blue hats.
Yes.
And, okay, and then all of a sudden you're going to find out which of them have all of a sudden you're going to find out which of them have red gloves and which of them have blue gloves. And
And it's going to be like, what can I say? It's going to be very much like a random choice. You know what I mean? It's like, what proportion, yeah, right, what proportion of the red-hatted people will end up getting red gloves?
Or A?
Is that a proportion? Is A a proportion?
A over
A
A
over-
over C times E plus G.
I mean, A over number R.
Yeah, I guess A out of that or something.
Times E plus G.
Oh, you're trying to, now you're trying to go ahead and do the answer.
That number are no, that number are
Well, we're not even down to the shoes yet.
Yeah, but he's jumping ahead because he's got an idea.
Okay.
times number are
So, it sounds right, it sounds like he's trying to multiply probabilities together.
Base. And
And,
that's called Baez something, right? The Baez rule or Baez theorem. Yeah, this conditional probability
that might be true, okay, that might be true. I'm not sure if this is going on here, but that's an interesting idea. So,
What is this you just wrote down? You wrote down the proportion of them wearing red
The people with red hats
gloves,
that are
right?
gonna have red gloves.
yeah, this is
Yeah.
like the proportion,
Oh, yeah.
the proportion of the red-hatted people who will become red gloves as
Mhm.
well. And then the ones who will become blue gloves instead will be,
Uh-huh.
Then you write E there. So yeah, AD, so yeah, you write AD.
C over, yeah.
So it's AD plus CX over number R. That's what you want to put there.
okay, this is interesting. So where do I want to put this? Right
Right
here?
there.
What do you want to put?
AE,
A-E?
yeah,
Yeah,
plus CX
yeah.
over number R.
That's really right.
Well, if it is, now he really is doing some sort of matrix multiplication. Is that an
Yeah.
accident?
That is this conditional probability.
Yeah, okay, so, right, so people are already guessing the obvious guess here. It's a very peculiar guess, but very close to the correct, that we're going to be doing, in effect, some sort of matrix multiplication here. And I'm going to go ahead and give what I think is the correct answer for how this works. All right, over here. I think if you multiply the matrices together like this, it will give you the sort of central tendency, where the probability piles up. Now, okay, so first of all, it's possible, it's maybe even probable that I have somehow gotten my matrices, my horizontal and vertical switched from the way some other people do it. I don't know. But aside from that, you should be able to multiply these. So I'm going to say it is almost just like multiplying this matrix by this matrix. That's one minor little thing that gets in the way, which is this matrix, which is sort of like, I mean, we're sort of doing this. We're sort of composing arrows here, rather than. I don't want to draw the Young diagram of 200. I don't want to draw 200 boxes and then 100 boxes and 100 boxes. I'll just write like 200, 100, 100, and then 200, 100, 100, and 200,
I'm sorry. Sorry. Okay, so let's write it down. Write it down as R, number B. That's the Young diagram. So,
Yes.
and then in the middle, we have the Young diagram
Yes.
with R prime and B prime. And then over here, we have the Young diagram with R double prime and E double prime. And over here, we have this matrix and this other matrix. So we have the matrix A, B, C, D, E, F, G, H. But the way it works for some strange reason is that the thing in the middle sort of contributes its own little thing, which is just this diagonal matrix, which sort of it normalizes things in a funny way. That's what this thing in the middle is. It's associated with this thing in the middle here, so sort of this Young diagram. And again, I just think of it as some sort of normalization trick that comes up. That you have to deal with it at some point. So, okay, let's calculate this matrix product and see if it comes out. Yeah, right, this is a way of checking our calculation over here. We started doing the calculation here by sort of thinking real hard about it. And now, this is the way I think you're supposed to do it. I want to check this calculation against this little prediction that we had over here.
It depends on,
Yeah.
your rows and the columns, I don't know. Over here, I would assume that you're multiplying this on the left and that on the right.
Say that again?
Or wait. Actually, yeah.
Sorry, I should put numbers here. I forgot to put some numbers on there.
Sorry, no, that's fine.
It's like R, B, R prime, B prime, R prime, B prime, R prime. Something like that. Yeah, I guess I'm a little bit worried. I mean, you guys divided by R. Is there any hope that it could actually make it divided by prime?
Oh.
Why did you get R? I don't remember exactly.
You get that.
So what do we get over here?
So the first entry there is AE over R prime plus, so that AE over R prime
What's the number of R prime? Yeah.
plus BG over number B prime. The first, because on the first two matrices is just simply dividing A and B by R prime, and dividing A and C by R prime, dividing B and D by B prime. So then you just got it makes multiplication of AE plus BG.
Can we go back to can we go back and test it on this example? Let's test it on this example over here. See if my formula works.
Okay.
On this example over here. So I guess I'll do it over here. I guess. So we're going to have $100, $100, $100, $100. Here we'll have 1 over 200.
Yeah.
Over 100. Here we'll have okay. Now what do we get for the answer? be good at matrix multiplication? I'm not.
Well, it's got a lot of zeros here, so it's not that difficult. So your first column would be,
Do you want us to do it backwards way, like he did these up here?
I think it actually doesn't even matter, it's just symmetric or something. But, yeah, I was trying to sort of follow this system that I had
Okay,
here.
so the bottom corner is 100.
Bottom corner here?
Yes.
Yeah,
And the rest are zeros in the same row and column on it.
yeah.
I've done myself.
Okay.
Let's take the top left corner, that's not too hard to count, calculate. That was about 200, so.
Top
So are you trying to do the whole three?
Let's
Whole
just
time?
do it.
I'm going to do two at a time.
How about the one, two, and
The
three?
first one, I mean, when we find this matrix, the first one is, I mean, the first one stage is really, so that bottom corner is actually one thing, if you want to do it the first thing. So just multiply the first two, you get one.
So what are we do?
Yeah, we do the first two together, right? So you get a 1/2.
Well, all I'm saying is, it's a block matrix
One half
anyway,
of there,
you know what the
no?
last entry is.
Yeah. 1/2. Yeah, I was trying to go,
Okay, no, that's-
that, the next one down would also be 1/2.
1/2, yeah.
The next two over here, 1 and 1, 0. No, that's
That's
0.
fine.
That's zero, okay. And then
One, zero,
One,
and one
zero.
are the limit.
Say it again?
1,
1?
0,
Zero,
and then a 1 in the corner.
and then 1 then?
Now multiply by the third matrix.
Okay. So what do we get?
Right, by the third one, that's one. 100.
You get 150 in the top corner.
You do? Where?
Yeah.
This matrix and the third matrix which you want.
And you get 50 in the next entry on that row.
50 and
I'm confused.
You get this matrix.
Okay, that's, okay, so say again, 150 where again?
That's right. You
Oh,
get-
you're saying that?
Yeah, it works out.
I'm just a little bit, are you sure you didn't switch horizontal and vertical? Again, it wouldn't make much difference. You sure you didn't switch? Because right, you're saying this labeling sort of indicates which way the horizontal and the vertical go. Are you sure you didn't switch it at some point? Again, the answer would come the same way either way, I think, because it's a symmetric matrix, isn't it?
they're all symmetric matrices. So
Yeah,
the
but,
particular
but,
is
no,
one.
no, I'm agree.
Okay.
Yeah,
Okay. So, yeah, so I think this is the right formula. So, is it really coming out this sort of ugly?
maybe it is.
Okay. Well, I guess the answer is whatever it is. I mean, it's just this.
Why is that? Is there some, I guess easy to see way like the most likely.
Well, it's the arguments you were giving here. It is the arguments you were giving here. So, I mean, I'm not sure I can completely justify it right now. You guys actually completely justified it in this example over here.
Yes.
I was trying to just sort of think of it in an intuitive way. Again, I was trying to tell this story. Can you imagine? You can just see the hats first, and then you sort of, then you see the gloves show up, and it's almost as though each person is deciding independently of the others what color gloves they're going to have based on what color hat they have. It's almost like everybody's acting independently, except it can't be completely independent, because if we're completely independent, then you might not get exactly the right number of hats, right number of gloves of each color. So it's like there has to be some sort of cooperation between them, so that they know that they're going to get the exact right amount of gloves of each color. But aside from that, it's as though everybody is just randomly choosing
choosing according to these probabilities that we were talking about, what color to switch to.
So here you have R and here you have R prime. What are your, what's right? I think.
Okay, let's
gonna make a much longer
try to fix that. Let's try to fix that problem in a moment. But first, let me just try to state again what I think is going on here. What I think is going on here is I sort of told a sort of story about how to think about what's going on, and the way the story works is that when you do the exact calculation, there are some really hairy correlations between the way the different people are behaving.
Yeah.
But when you go ahead and do the approximate calculation, you just ignore the correlations between the way the people are behaving. And you just pretend each person is acting independently. And then it becomes a simple probability problem that you can use transition probabilities for. And this calculation, you can really just think of it that you have transition probabilities, and you're composing matrices of transition probabilities, and they're slightly normalized.
Yeah, right. I mean, I can understand the transition matrix between states.
Yes.
What's that thing in the middle?
That's normalizing the probabilities. That's normalizing the probabilities.
But in a sense, like you said before, that's not necessarily normalizing it the way we would normally want to.
Okay, I think I might know what's going on here. I think I might know what's going on. Let me tell you what I think is going on here. Let me tell you what I think is going on here. I drew this picture over here.
Yes.
I told you that the way the calculation works is that you associate matrix of transition probabilities to each arrow.
Yes.
And then you associate a diagonal normalization matrix to each thing over here.
Yes.
And there is really a matrix over here. Sorry. There's a matrix over here, which is like 1 over the number of R and 1 over the number of B. Sorry. Yeah, 1 over the number of R and 1 over the number of B. And there's 1 over here, which is 1 over the number of R. Diagonal matrix again is 1 over the number of R double prime and 1 over the number of B double prime.
Yes.
And see, you actually have different choices about how to do the calculation, and you have there are different normalization conventions that you can use about how to normalize the probabilities. And I think that's what's causing the problem here.
So you're wondering which one to use?
Yeah, I mean, sometimes people go,
Okay.
sometimes you can think of the problem, there's no real arrow of time in this problem, but you can put an artificial arrow of time in
And
the
that's the
problem.
problem here, because what we just did,
That's right.
you multiplied the matrices in a different order than what I did here. If you put them that way, and instead of using the R prime matrix, use the R and D matrix, the one that you just used here, then I think you get exactly what I wrote.
And I'm trying to think that
And-
the way you've written your order, your basic,
It should be wrong.
should be multiplied the other way.
Because of that,
If we're doing some composition, we work from right to left, I think.
Well, that's right. I think that's what I'm complaining about what you're
I think
doing.
that's exactly what you pointed out here, that's
Because the problem is
right.
right.
Yeah, no, but I did say at one point that I might have my horizontal vertical convention reversed from the way other people are doing it. But I'm just following the labeling here. So it's not like I'm trying to use anybody's convention. I'm just following the labeling to its best. And I think it got.
Yeah, so that's
That's the problem.
Oh, then it's wrong.
That's wrong. Yeah.
Oh.
No, because your matrices that you wrote down are wrong.
Are they wrong?
No, you're not wrong.
He wrote them in a different order than where you.
They're labeled, so it's
Okay,
labeled.
Okay, yeah, this is what John was saying last
Yeah,
time.
he's
Yeah,
multiplying.
I'm not deliberately trying to do it backwards from the.
Right, but you want to multiply that first, then this, as opposed to, the way you wrote it down, we all thought we should multiply this side, that, and that. But it should be multiplied in the other way.
Well, okay, but the way I'm thinking of it is I first look at their hats, then I look at their gloves, and then I look at their shoes.
Right, so all
And I just record in chronological order what I did. you
Yes,
know,
okay, yes.
And
Right.
you can do it that way, but you're telling me I should do it the other way.
But when you have matrices like that, they are multiplied in the other order.
Because we take these
But that's the convention.
Sure, so then the abrasive multicolor convention here does not make
Yeah, yeah.
any apples in the world use. Sure.
So,
Well, it makes no.
that's what I was trying to figure out. I was trying to figure out,
Yeah, so that actually is not the usual matrix product of these. It is
because I believe you, I honestly don't
Yeah,
know
yeah.
what the usual convention is. Okay. So, I'm not deliberately
No,
trying
no,
to
no,
do that.
sure.
That's fine.
Now we I think we figured it out, why.
Okay, okay, so
In
maybe,
fact, this uses that first R and B matrix, not R prime and B prime, and if you did that, you would get.
yeah. Okay, see, the way I'm thinking of it, I'm thinking of it, you go like this and like this, and you're telling me that.
Yes, that is true, yeah.
Okay.
We weren't doing that, we were.
Okay, so that's not what you were doing.
Exactly. That was-
Yeah, I would.
Okay, okay, and that's what I got confused over there.
Yeah, so you're right, just that one and that one half over here is switched and this one.
Okay, I'm sorry about the confusion, I was trying to avoid confusion.
Finally, we have it.
Okay, so, so can we figure out what we're getting here? We're getting A, like, A plus CF?
Yes, A plus C. But we said so R prime.
But what's the normal?
R prime, not R prime.
The whole thing is divided by,
The first one is divided by number of prime.
by R prime?
Yes, yes. Yes, R prime. They're all R prime. It's the one essential, there can be no reason that it is.
Yeah, it's, the whole thing is divided by number R prime.
The whole thing is divided by R prime?
He wrote from HC,
Still
like a mirror and
so.
universe.
On column and
I guess, I don't know.
I think this is what I was
A
saying.
times 1 over R prime plus B times 0.
So, do you think this is right? I understand all stuff here.
I think it's right because.
We should really be doing this, we should multiply.
Okay, can I write this on the board?
Yeah?
Would it be right? Okay, just because we want to be. So what I was trying to say is,
Yeah.
I think we want to do it
for, you can make
The way you understand
one
one
side or the other, is to multiply them by any composition or either right or left.
Yeah, and I'm using chronological order.
Right, so in order to look at this and having me understand how to make these multiplied, we should write them in the order that people use them.
Now what?
The problem is, if I do that, I'll get it backwards. I'm just not used to doing that. So,
Okay.
I understand where you're going now.
okay. I'm not trying to cause a problem, I'm just trying to, see, if I put the extra label in on, you should be able to tell which way I'm doing.
Yeah.
Okay.
I agree with that answer right there.
I was using.
So,
Because of C, because of C.
so what else are we getting? We're getting AG plus EH.
This solution.
And the AG is over, now this is the one that's going to be over 2 different things.
Oh, is it? I don't know.
Yeah, it's going to be AG is over,
But
the AG is over,
really is much like yours. No, we must then.
the AG is over, R prime.
But we do this.
And it looks like the CH is over B prime.
Okay. Right, okay, so I guess we should try to state, okay, for the benefit of people who really want to stick with some traditional convention of matrix multiplication, we should state what this would look like when you write it according to the same.
Exactly.
So it would be the same thing except we, two would be six?
Yeah.
So, yeah, I mean, if you stare at these labels and think about what you're doing, right? I mean, right, these two are these two, and that tells you, right? You need to figure out what my convention is by
We have to
looking at that.
multiply the
these
column of
two.
this one times the rows of that one. Right?
Yeah. But, you know, these two is the same as these two, and then as well, these two and these two, yeah. So what is the point of what we're doing here? The point of what we're doing here is that we're we're doing an approximate calculation of composition of Hecke operators. That's what we're doing here. We also talked about how we can do a more precise calculation. But here we're doing an approximate calculation. And in fact, you could say that what we're doing here is an approximate calculation in a certain limiting case. Right? This is an approximate calculation we're doing. But as you put more and more zeros on the ends of the numbers, on the ends of the matrix entries, this approximate calculation that we're doing becomes more and more precise. So what we're saying is that there's a certain limiting case where the composition of these Hecke operators turns into ordinary matrix multiplication, or perhaps I should say ordinary matrix multiplication with a little extra fuzz factor in it, normalizing things in the middle. Okay, so this is one of the things that is suggested by the matrix notation that we mentioned. I started introducing this matrix notation for Hecke operators, and I described it as a suggestive notation. And it's suggestive because it hints that there's a certain way in which you can think of the Hecke operator as being like matrices. And here we're seeing one of the ways in which this suggestion is a good suggestion. Because the composition of the Hecke operators is a sort of imitation of matrix multiplication, at least in a certain limiting case. The composition of these Hecke operators, these ones that look like matrices, is an imitation of matrix multiplication. And that's not actually the only way in which these Hecke operators that look like matrices behave like matrices. There are some other ways in which these things that behave like matrices also act like matrices. And we'll probably try to talk about those at some point. And it's also not the only notation system that we're going to introduce for Hecke operators, for these Hecke operators. We're going to introduce another system of notation for these Hecke operators, which is going to be also very suggestive, but suggested in a different direction. But I don't think I can do that right now. We don't have enough time right now. So I just want to make one last comment here, which is that we did all of these calculations, all these approximate calculations, we did them all under the assumption that we were working just with flags on finite steps. We also know that we can talk about flags on vector spaces, finite dimensional vector spaces over finite fields. And I stated that the matrix notation actually works to describe the binary relationships between flags, the binary Hecke operators. It works even for the flags on finite dimensional vector spaces over finite fields, not just for the ones that we're thinking about here, which are on finite sets. So that means that whatever calculus we're inventing here for the composition of Hecke operators should have a version that works for the Hecke operators between flags on the vector space instead of the flag on the finite set. So that turns out to be true. That everything that we're doing here today is sort of just the Q equals 1 special case of something that you can do much more generally, where you allow Q to be the size of any field, any finite field. And I'm going to quit right there.